Evening, please do attend class because exothermic, endothermic, the collisions in the nuclear physics that I'll be discussing. It's a very important, again, the type of asking questions in advance. Please don't miss. A star has initially 10 to the power of 40 deuterions. It produces energy via the process. Two deuterions will combine to form helium isotope. Again, open the deuterium will combine with the tritium to form the final, the helium and one neutron. You can see here neutron is there. The average power radiated by star is 10 to the power of 6 watt. The deuterium supply of the star is exhausted in a time of order. Per second, it will give this much of energy. And these many deuterions are there. So for what time the star will survive? So all the deuterions will get exhausted. So what we have to do? How much of energy is generated in this reaction will calculate. I think there's a proton. No? How much of energy generated in this reaction will calculate. How much of energy generated in this reaction. So we'll get that energy here. Then we have this particular power. There's a power that one. Per second, how much of power that one. And other side, we have the initial number of deuterions. First, we'll calculate energy release in the first reaction. So this energy released here, let it be Q1. We'll calculate this Q1. Q1 will be mass of deuterion need one. This helium is needed, no? I think it should be tritium, not helium isotope. I'll change the symbol. I think this should not be there. Okay, fine. I think that will be correct. Oh, we have data problem. Anybody check book? I think question itself. I'll just check once. It's a previous advanced paper. Oh, this is something. H3, it should be one H3 only. Yeah, fine. 1H2, 1H2, 1H3. Yeah, this much of information is available. Okay, no problem with that. Now the He, not He, it should be 1H3, tritium. First we'll calculate Q1, but we don't know this 1H3. No, I think you just do one thing. Add up these two. Total energy release will get it. Because 1H3 is there here, it is there in RHS, it's there in LHS, that one. So what we should do is the total energy released in the combined reaction. Better you go for take help of equation like this. So the total Q1 plus Q2 is what? The total energy released. In that, I think 1H3 on either side will cancel out. No need to search for that particular information. You can now substitute this. This will be, I think, 3H2, 3 times of 2.041 U minus, this will be helium 4.001 U minus mass of proton neutron. No? So this is 1.008 U. So we'll do one thing, delta M will calculate. Later on I'll write it. Mass of proton should be less, no? Some data. 7 you write it, no problem. Mass of proton should be less than that. We'll proceed like this. Huh? Okay, let's do it. So we'll subtract this. So this will be 2.014 into 3. 6.042 minus of, we'll add up this to 4.001. It's an objective question. You are permitted within 3 or 4 minutes. You're supposed to wind up. 6.0. I say don't do approximation. I think this is something very crucial for you. Don't do approximation. You see 6 minus 6, 0 will come. The third decimal place is what it matters here. Second and third decimal place. So this will be 0.026 AMU. So what is the energy released will be? Total energy released will be delta M C square. So 0.026 1 AMU. I think we'll take it 930. We'll make it round figure. So 0.026 930 into 10 to the power of 6, 1.6. These many joules. 930 into 1.6 into 0.026. 38.688 into 10 to the power of minus 13 joule. Per deuteron, so this is there 10 to the power of 40 deuterons are there. Per reaction, what happen? We'll get this much here. How to proceed now? What is the power radiated for every 1 second? 10 to the power of 6 joules it will radiate. And for every reaction, 3 deuterons are being used. For every reaction, 2 deuterons. So he's asking what is the time after which the total mass of the deuterons will get exhausted. How to relate that 10 to the power of means 10 to the power of 40 deuterons, how to bring? I think till now we were just focusing on what, like the energy released, no? How to introduce that particular, the mass of the amount of deuterium. For every reaction, this one. So how many reactions should take place? You check it. Per reaction, 10 to the power of 40 deuterium. So how many reactions should take place here? So that how many reactions per second? So in 1 second, how many reactions? Or so like per second, per reaction, 3 deuterions. per reaction 3 deuterions. And per reaction, how much? This much of will be there. Then for 10 to the power of 6 reactions to occur, what is the time taken? You calculate. So from that, we'll get the number of deuterions to be exhausted. What is the time taken for 10 to the power of 40 deuterions to get exhausted? We can determine. And just calculate that. And I'll anybody answer?
into 10 to the power of 22.
1.298 10 to the power of 22. I'll check the key. Wait. Let me check it.
10 power 6, sir, answer.
Ninth one. I'll check it answer. Huh?
Sorry, 10 power 8.
Ninth one C. 10 to the power of 12 is telling that 1.29 you can neglect, no problem.
10 power 22 I'm getting, sir. That's
22, sir.
22 we are getting, sir.
22, huh?
Yes, sir. 22. 1.29 into 10 to the power of 22.
10 to the power of 40 deuterions you have taken.
Yes, sir. 10
Sir.
power 40 on. We'll take 10 power 30. That time we'll get 10 power 12.
Sir, question it should be 10 power 16, sir. Average power.
Which is average power? I'm not
In the question,
10 to the power 16, huh? Oh,
sir.
I didn't. Oh. No, that's why it's not matching. 16 I'll make it. Then okay. This should be 16.
Sir.
Oh, question itself is wrong. I think now okay. Check it now. No.
Yes, sir.
Okay,
Now,
sir.
Ah, 10 to the power of 12, that 1.29 you can neglect. I think 1.29 will come if you do calculation. Till here, okay, 3.8 into. This is okay. We have done calculation, I think no problem. No. 10 to the power of, now 10 to the power of 40 deuterions per reaction, 3 are there, no? 10 to the power of 40 by 3 into this much you take it. So you'll get the total energy. So I'll proceed further. 10 to the power of 40 per reaction, how much 3 are there, no? And how much it is? 38 point. So this is the total energy released by the deuterions. Now what is the average power? The average power radiated by star is equal to 10 to the power of 16 watt. Calculate its energy. Let it be this one. So I think now you can bring the time, no? Anybody value of this? ET is how much? Anybody give value ET? I'll wind up this problem then.
ET will be 10 power 16 into T only, no, sir.
This is no 10 to the power of 4 by 3, this value. Total energy released by the deuterions.
1.29 into 10 power 28.
1.29 into 10 to the power of 20. Okay, now we have this one. No? This is the power what we have now, 10 to the power of 6. So can we bring the time? Time is equal to this ET by power you bring it. power radiated by the sun. I think I'm just using some typical symbols. Is it okay? Fine. This way you are supposed to think. Power watt, energy by time, no? That, so we'll get in RHS the time factor here. So 1.29 into 10 to the power of 12 seconds, approximately. Yeah. Okay, the correction is there. Please do notice. Like this, questions can be asked. It's already there in advance. Possibility of asking again in different way. So just do practice. This is very important. Fission, fusion. This one, I think straight away questions are there. Evening, I'll discuss the exothermic endothermic reactions. That one. That's also very important. Please don't miss class. 6 o'clock we'll have. And Satish sir will take anything. Any syllabus pending is there? Anything?
No, sir. Over sir syllabus.